In this video, we'll cover buffers. Buffer solution is a solution that resists change in pH when a small amount of strong acid or a strong base is added. Take a look at this particular image. So if you have a solution right here and there is some kind of substance in there, and in that substance, you add in a very strong acid, okay? Well, originally the pH, let's say, was 3. And if I were to put in a very strong acid, we would assume that the pH would diminish, maybe to a 1. However, in a buffer system, what happens is this doesn't happen, but it might only go to maybe 2.99, maybe even remain as 3. So again, a buffer solution is a solution in which that prevents that pH drop to happen significantly or prevents pH to increase significantly. Buffer solutions are made up of weak acid and its conjugate base. For example, we have this acetic acid and acetate pair. The acetic acid, its conjugate base is the acetate. Another example would be something like this. You can have a very weak base and its conjugate acid like ammonia and ammonium. Ammonia and ammonium are weak base and weak acid respectively. Here is a better image to show you what's weak acid and weak base. If you fall under this category right here, under these two brackets, they all are pretty good, I would say, buffered solutions. So if I were to have HF and its counterpart is F minus, HF is the weak acid and its conjugate base is F minus. So having these two weak acid and its conjugate base, when they both have its counterpart, we consider this having a buffer solution. So anything fall that under this bracket in here. A buffer system can be further calculated by utilizing this Henderson-Hasselbalch equation, and that's represented like this. If you have a system where you have a weak acid and its conjugate base right here, we can use this Henderson-Hasselbalch equation in order to find the pH even before the acid, even before the base has been added. And you can also utilize this after it has been added as well. But we have to look at what are all these represent. So pH is equal to pKa plus log of A minus and HA. Well, the pKa represents the negative log of the Ka value, so the acidic equilibrium constant, right? And you can find that on your reference sheet, and it's that chart of Ka dissociation constant. Then you have the A minus. The A minus represents the concentration in molarity of the conjugate base. Then we have the HA, which is the concentration of the weak acid in molarity. We're normally used to having acid on top and the base on the bottom, but please note that the base for this particular equation is on the numerator and the acid is in the denominator. And we utilize this particular equation as with buffered solutions. So not so much in a strong acid or strong base, but something that is in buffer solution. Let's do a learning check based on what we have learned so far. Here it wants to know what is the pH of a solution that is made from mixing 50.0 ml of 1.5 molar hydrofluoric acid and 30.0 ml of 0.80 molarity of potassium fluoride. If you can't tell, but the hydrofluoric acid and potassium fluoride are actually weak acid and weak base, its conjugate base counterpart. But you'll notice that K is there. Now that K is considered to be a spectator ion, and so therefore we do not consider them part of the equation that we will look at now. So HF, is the weak acid, and its counterpart is the F minus, right? Because K is plus and fluorine is minus. That's why these two represents this one. But if they're in a solution, they're separate apart. And this is what it represents in a solution. And we know that potassium is a spectator ion, meaning it does not participate in any reaction, so therefore we ignore them. On how we can detect which is spectator ion and which not, we'll talk about that towards the end of this learning check. Let's move on from here. Now it wants to know what is the pH of the solution. Well, before we go into anything, we want to know what's happening in solution. So if you have the hydrofluoric acid in solution, which means that it's in water, okay? So this is aqueous, here's my water in liters. And because hydrofluoric acid is considered to be an acid, weak acid, it will donate its hydrogen to the water, forming into F minus, and then you have hydronium ion. If we want to know the pH, we'll probably have to know the concentration of the hydronium ion. But notice that we have mixed the HF and F minus together, meaning that something has been diluted, that the HS have been diluted, and so has F minus. When we think of dilution equation, we can think of the M initial, V initial is equal to M final, V final. I representing initial and F representing final. So let's talk about the HF first. So initially, it was 1.5 molarity, okay? Initially, the volume was 50.0 ml. Then we want to know M final, which is the molarity after it has been diluted with its conjugate base. And the V final is the total amount, so 50 plus the 30 ml. So that would be total of 80.0 ml. We want to know molar final, MF. So therefore, we divide it by 80 both sides. And go ahead and calculate, let's calculate this out. 1.5 times by 50. And then I'm going to press enter and then divide it by 80.0. And you should get 0.94, okay? 0.94. 0.94 molarity. That's my concentration of HF, the weak acid, when after it has been diluted. How about fluoride? So what about this guy, right? F minus. Well, F minus, that also is diluted, so we also need to utilize the concentration equation. So for initially, it was 0.80 molarity. Volume initially was 30 ml. And we want to know the molarity final concentration, and we know the total volume is 80. Okay, total, that's what happened in the end. So we're going to again divide 80 both sides. And then go ahead and punch this into the calculator. And then if you were to punch this, you should get 0.30 molarity of F minus, okay? So we know that so far, but we haven't found the pH yet. Well, we remember that right before this particular slide, there was the Henderson-Hasselbalch equation, which gives you a very nice setup where pH is equal to pKa plus log of HA, which is or A minus, which is the base, and our base is F minus, and our acid, which is our HF, concentration units. pKa represents the log of HF. And if you were to go back into your reference sheet, find HFKa. So if you were to find that, you should get 6Ka should equal for HF should be 6.8 times 10 to the negative 4. So this is a value that's in your reference sheet. And so pKa represents the negative log of this, 6.8 times 10 to the negative 4, plus the log of F minus at its final state, which is 0.3, divided by the HF, which is 0.94. Okay, so let's go ahead and plug all of this into our calculator. I have negative log of 6.8 times 10 to the negative 4. Okay, and then I'm going to press enter, and then you're going to add log of the 0.30 divided by the 0.94. And I get 2.67. So my pH is 2.67. I want to add on how you can determine what is a spectator ion within a compound. So say you have an acid like hydrochloric acid, HCl. Or a base like NaOH. We know that it is the hydrogen that is being donated that allows for this entirety to be an acid. That means the hydrogen is an active participant of the acidic equation. However, its counterpart, which is the chlorine is going to be the spectator. For example, for NaOH, we know that the OH is going to be the one that's going to accept the hydrogen, meaning that if I were to split this off into its ionic form, hydroxide and sodium, hydroxide is a strong base in which it's going to accept the hydrogen. So that means its counterpart is a spectator. So for an acid, it is donating the hydrogen. For a base, it's accepting the hydrogen. Well, we know that sodium wouldn't be accepting the hydrogen because hydrogen is plus charge and so is sodium. So it must be its counterpart that's going to be accepting the hydrogen. So therefore, we know that this hydroxide is the active participant in order for acid-base reaction to occur, whereas the other guy, its counterpart, is the spectator. By definition, a strong acid and strong base, its counterpart is going to always have a spectator ion. Well, next, do another example. H2SO4. This sulfuric acid is considered to be a very strong acid. So when it loses hydrogen, both of the hydrogen, you're left with SO4 2 negative. And SO2 negative is going to be your spectator. So this is your counterpart and this is your acid portion. So I hope you can sort of determine which one is a spectator ion and which one is not based on what you have learned so far.